Okay, in this lecture we're going to cover our section 4.4 material on the logistic equation, which will be a more realistic model for population growth than the exponential growth model. So to introduce the logistic equation, let's consider the following example. Let us suppose that y of t denotes the population size of some species at time t, which is non-negative. And let us suppose that the rate at which the population changes, that is, the derivative of population size, is given by the differential equation ry times 1 minus y over k for our derivative dy dt. And we have some initial condition, y of 0 is equal to y naught, where r and k are positive constants, and y naught is some non-negative value which represents the initial population size, that is the population size at time 0. So this initial value problem is called the logistic growth equation, or in particular this differential equation is called the logistic growth equation, or sometimes simply just the logistic equation for short. So in part A of this example, we're asked to solve this logistic growth equation. Now, this equation is a separable differential equation, so I could solve by making use of separation of variables. If I move everything involving y to the left-hand side of the equation with the differential dy, I have dy over y times 1 minus y over k. And if I move everything else that is not involving the variable y to the right-hand side of the equation, I've got r times dt. Now, one thing I don't especially like here is the fact that on this left-hand side I have a compound fraction, that is a fraction within a fraction, in my denominator. So to eliminate that fraction within the denominator, I'm going to multiply the top and bottom of this expression by k. So I would have k over y times k minus y dy, and that's equal to r dt. So just rewriting that expression on the left-hand side. So to solve from here, I need to integrate on both sides to eliminate the differential dy and dt. And if I make use of a partial fraction decomposition, this integrand on the left-hand side, which has distinct linear factors as its denominator, can be decomposed as 1 over y plus 1 over k minus y dy. And that has to equal to the integral of r dt. So I've used partial fractions here. Now, finding the antiderivative on the left-hand side of this equation, I have the natural log of absolute value y minus the natural log of absolute value k minus y is equal to rt plus c. And in order to solve for y, on the left-hand side of this equation, I'm going to combine the difference of these two logarithms as the natural log of the quotient y over k minus y. So recall from properties of logarithms that the difference of two logarithms with the same base is equivalent to the log of the quotient of those two values. And now, to eliminate the natural logarithm, I can exponentiate both sides with a base e, and I would have the the absolute value of y over k minus y is equal to e to the rt plus c, Or using properties of exponentials, I can rewrite this as e to the c times e to the rt power, where this exponential e to the c is a new arbitrary constant, so let's just call it c. So we have the absolute value of y over k minus y is equal to c e to the rt, and to eliminate the absolute value, I could take positive or negative c e to the rt power. But now this positive or negative value of c is just some new arbitrary constant, so let's simply call it c. Now from here, I can solve for y by multiplying both sides by our denominator, k minus y, and expanding. So I would have on the right-hand side a ck e to the rt minus c e to the rt times y. So grouping my y terms together, I have y plus c e to the rt times y is equal to ck e to the rt. And then factoring out a y, I'm left with 1 plus c e to the rt is equal to ck e to the rt. And solving for y as a function of t, I have ck e to the rt over 1 plus c e to the rt. Now, this is my general solution of that logistic growth equation, but I also had an initial condition in this problem. Y of 0 was given as y naught, which represents the initial population size. And I'm going to use that initial condition to solve for c. Now, to save myself a little bit of work, rather than substitute t equals 0 into this equation, and then setting this equal to y naught and trying to solve for c, if I'm a little bit clever, I can make use of one of the earlier lines of my work. And if I substitute t equals 0 and y equals y naught into that equation, I have y naught over k minus y naught is equal to c times e to the 0, which is 1. So using that earlier line of my work, I immediately am able to find c, which is y naught over k minus y naught. And now taking this expression for c and substituting into the solution that we just found, we have y of t is given by c, which was y naught, over k minus y naught times k e to the rt. So let me write this as a single fraction. And I've got y naught k e to the rt over k minus y naught over 1 plus c, which is y naught over k minus y naught times e to the rt power. So this is the solution of the logistic growth equation. However, we can see that this solution is a little bit messy. In particular, it involves compound fractions again, fractions within fractions. And notice that in the numerator and denominator, these fractions that we have the same denominator k minus y naught. So if I take this equation and I multiply the numerator and denominator by k minus y naught, I'm left with y naught times k e to the rt over 1 times k minus y naught plus y naught e to the rt power. So this, of course, is a much simpler form of the solution of that logistic growth model. And what you'll sometimes find people will do to simplify this expression a little bit further is the following. So we notice that we have in the numerator and denominator expressions involving e to the rt power. So to simplify this a little bit, I could multiply the numerator and denominator through by e to the negative rt, or equivalently 1 over e to the rt. And I'm left with y of t is y naught times k over k minus y naught times e to the negative rt plus y naught. So this would be the solution of that logistic growth equation, or if you prefer, you could use the line above as the solution of that logistic growth equation. They're equivalent functions. So in part B of this example, we are asked to determine the limiting behavior of the population as t approaches infinity. So that is, what is the limit of this y of t function that we just found in part A as t approaches infinity. And then we ask, what is the biological meaning of the constant k? So here, as time t becomes infinitely large, our solution y of t, let's see what we're approaching. Now, the only term involving t in our solution was this exponential, e to the negative rt in the denominator. Now, since we have e raised to a negative constant multiple of t, as t increases, we have exponential decay, and this term will decay to 0. So our numerator is the constant y naught times k, and our denominator is approaching 0 plus y naught, which is just y naught. So we can cancel a factor of y naught in the numerator and denominator, and we see that the limiting value of the population size is k. So then we ask, well, what is the biological meaning of the constant k? So as we've seen in our solution, and by taking the limit of our solution, over a long period of time, our population size will approach this constant k. So here, the biological meaning of k is the following. K is the limiting population size. Now, if we think about comparing this with the exponential growth model, we saw for exponential growth, as time goes on forever, the population size will increase without bound. It becomes infinitely large, which we said was not very realistic. Using this logistic growth model, as time goes on forever, or as enough time passes, our population size is approaching some constant value k, which is a limiting population size, or we can think about this as the maximum sustainable population size. Now, this constant is given a special name. It is referred to as the carrying capacity of an organism, which is defined as the maximum population that can be sustained indefinitely within the environment. So of course we can't have an infinite number of any organism because we have a finite amount of space and resources like food, water, shelter. So the carrying capacity is defined to be the maximum sustainable population of an organism in some given environment. And that is what this value K represents, that carrying capacity. So let's look at some examples now, making use of the solution of the logistic growth equation and what we found about the limiting value. So in this next example, we're told that a population of rabbits in a meadow is initially observed to be 200 rabbits. And after a month, the rabbit population is observed to have increased by 4%. So assume an initial population of 200 and a growth rate of 4% or 0.04 with a carrying capacity of 750 rabbits. So within this particular meadow, we are assuming that there cannot exist more than 750 rabbits. So in part A, we are asked to write the logistic equation and the initial condition for this population. So thinking about the logistic growth equation, we had dy dt is equal to r, which represents our growth rate, in this case 0.04, times y times 1 minus y over k, where k was the carrying capacity, and in this problem we were given a carrying capacity of 750 rabbits. Now we also have an initial condition, y of 0, that is the initial population, is equal to 200. So this would be the logistic equation together with the initial condition for this rabbit population. So in part B, we ask what is the predicted population size, y of t, after t months. So we want the solution of this differential equation. Now, rather than go through the work that we did in our first example, every time that we see this logistic equation with different constants, we can use what we found in our previous example for all problems moving forward. So we know that the solution of the logistic growth equation with an initial condition, y of 0 equals y naught, is given by this y of t function that we found in part A of our first example. So taking the values that we have for y naught, k, and r, and substituting them into that equation, let's see what we have. So again, from what we found in the previous example, y of t is defined as k times y naught over k minus y naught times e to the negative rt plus y naught. So substituting in the values that we had, well, our carrying capacity k was 750 times y naught, which was our initial population of 200 rabbits. And then we're dividing by k, which was 750, minus y naught, which was 200, times e to the negative r. Now our growth rate here was 4% or 0.04 times t plus y naught, which was 200. So simplifying this just a little bit, let's see what we have. So in the numerator, our 750 times 200 will give us 150,000 over the 750 minus 200 would leave us with 550 e to the negative 0.04 t plus 200. So this is the solution of the logistic growth equation that we had written down in part A for this particular rabbit population. So now that we found that solution in general, in our first example, we no longer have to go through all that work of using separation of variables and partial fractions every time that we see this equation. We can just substitute the constants y naught, k, and r into the equation that we've already found, and we've got our solution immediately. Now, in part C, we're asked to predict the population after 1 year. So let's be a little bit careful with our value of t. So here, recall that our growth rate was measured in terms of growth per month. We noticed that after 1 month, the population increased by 4%. So our growth rate, R, is 4% per month. And so in part B, the expression that we found for the population size is the number of rabbits after t months. So if we're interested in the population after 1 year, we're going to evaluate our function at t equals 12, since 1 year is 12 months. So here, y of 12 is given by 150,000 over 550 times e to the negative 0.04 times t, which is 12, plus 200. And using a calculator to evaluate this expression, we find that the population size after 1 year is approximately 278 rabbits. Rounding to the nearest whole number, since we can't have fractions of a rabbit. Now in part D, we ask the question, when will the population reach 400 rabbits? So let's take a look. Here, we would take our expression for the population size at any time, which we found in part B, to be 150,000 over 550 times e to the negative 0.04 t plus 200, and I want this population size to equal 400. And now my goal is to solve for t. So I could start by multiplying this denominator across to the other side, and then dividing both sides of this equation by 400. So on the left-hand side, I would have 150,000 divided by 400, which gives me 375, and that is equal to 550 e to the negative 0.04 t plus 200. So now I could subtract 200 from both sides and then divide by this constant 550. So subtracting 200 from both sides, I would have 175, and then dividing by the constant 550, I would be left with e to the negative 0.04 t. And recall that e raised to a negative power is the same as 1 over e to that positive power. So my own preference when I'm solving here would be to first take the reciprocal of both sides of this equation. So in other words, I would have 550 over 175 is equal to e to the positive 0.04t. And from here, to solve, I would take the natural log of both sides, giving me natural log of 550 over 175 is equal to 0.04t. So finally, to solve for t, I would divide both sides by 0.04, or let's think about this decimal here. 0.04 is 4 1/100ths, which would equivalently be 1/25th. So dividing by 0.04 is the same as multiplying by 25. So I have 25 times the natural log of 550 over 175. And using a calculator to round to the nearest value of t, we find that t is approximately 29, where we were measuring time in months. So approximately 29 months, just under 2.5 years, for this population to increase to a value of 400 rabbits, which is double the value that we started with. All right. So in our next example, we are asked for given the following information: a population of deer inside a park has an initial population of 60 deer, and the carrying capacity is 200 deer, and the growth rate is assumed to be 2% per month. Okay. So in part A of this problem, we're asked for the population of deer after t months. So here, using the expression that we found in our first example for the solution of the logistic growth model, we have y of t is equal to k times y naught over k minus y naught times e to the negative rt plus y naught. So let's substitute in the values that we were given in this problem. So k was our carrying capacity, which we're told in the problem is 200 deer, times the initial population, y naught, which was given as 60. And then we are dividing by k minus y naught, so that is 200 minus 60, times e to the negative r times t. Now r is our growth rate, which we were assuming is 2% per month, or 0.02 per month, times t, plus y naught, which was our initial population, 60. So simplifying this, let's see what we have. Through the numerator, we have 200 times 60, which leaves us with 12,000, over 200 minus 60 leaves us with 140, e to the negative 0.02t plus 60. All right. So this is the population after t months. So in part B, now that we have this, we ask when will the population reach 100 deer, which is half of the carrying capacity. So in order to determine that, we would take our function that we just found for population size, and we would set that population size equal to 100. and now we want to solve for t. So as we did with the previous example, we could start by multiplying both sides of our equation through by this denominator, and then dividing both sides of our equation by 100. So on the left-hand side, we would have 12,000 divided by 100, which gives us 120, and that would equal to 140 e to the negative 0.02t plus 60. And from here, I could subtract 60 from both sides, giving me 60 equals 140 e to the 0.02t. And then I would divide through by 140. So I have 60 over 140, or equivalently 6 over 14, or 3/7 is equal to e to the negative 0.02t. And again, I'm going to make use of the fact that e raised to a negative number is the same as 1 over e to that positive power. So I would take the reciprocal of both sides of this equation to get 7/3 is equal to e to the positive 0.02t. And now taking the natural log of both sides, I would have the natural log of 7/3 is equal to 0.02t. And to solve for t, I would then divide both sides of this equation by 0.02. Now 0.02, that represents 2/100ths, or 1 over 50. So to solve for t, I would multiply both sides of the equation by 50. That is equivalent to dividing by 0.02. So t would be given by 50 times the natural log of 7/3, or if we want to approximate this to the nearest month, this would be approximately 42 months for our population to reach half of its carrying capacity.